In today's lesson, we continue our work with angle identities. Today we're going to focus on what's called a double angle identity. When A equals B in the identities for the sum of two angles, the double angle identities will result. Let's take a look. We'll start with the cosine of 2A. So again, we're going to let the angles be the same. So that means 2A would be considered as A plus A. So filling in with the sum identity for cosine, that's cosine A times cosine A minus sine A times sine A, which cosine times cosine becomes cosine squared minus sine squared. So that's the first of our double angle identities, the double angle identity for cosine. But there's two other useful forms of this identity because we can use the Pythagorean identity that the sine squared A plus cosine squared A equals 1. Again, remember I told you we're going to use this one a bunch because it's so beneficial for us. And you have to be familiar and comfortable working with this identity in different forms. Yes, sine squared plus cosine squared equals 1, which means that cosine squared equals 1 minus sine squared, and sine squared equals 1 minus cosine squared. And if we substitute this into our new identity of the cosine squared minus sine squared, as you can see here, we're substituting in for cosine squared. These would be like terms, and we get an alternate form of that identity, 1 minus 2 sine squared of A. Here we're plugging in for sine squared, distributing the negative through, and then combining your like terms, we get 2 cosine squared A to A minus 1. So 3 forms of cosine of 2A that you need to be familiar and comfortable with. When to use which form? Well, we'll show you that in a minute. It's going to depend on what information that you're asked to find and what information that you are given. So there's the first of our 3 double angle identities. Next, let's look at the sine of 2A. So again, the sine of 2A would be considered the sine of A plus A. Using the sum of sine formula, which is sine A cosine A plus cosine A sine A. And again, since we're allowed to multiplication is commutative, we can rewrite this second identity, part of that identity, we can make it say sine times cosine if you wish. That way you can clearly see the like terms, and the sine of 2A is 2 times sine A times cosine A. And finally, here's our tangent of 2A. Again, here's the sum identity for tangent, tangent of A plus the tangent of B, where B is A in this case. 1 minus tan A times tan B, or since B is A. And then combining our like terms, 2 times tangent of A, 1 minus tangent squared of A. So now you can add these, the highlighted identities, and there are 5 of them. There's cosine of 2A, all 3 versions, and then the sine of 2A and tangent of 2A. So go ahead and put those into your flip book and make sure that you write down all 3 forms of the cosine of 2A because we're going to use all 3. How we're going to use it? Well, let's show you an example 1. First thing I expect you to be able to do with this is I expect we need to be able to find function values for 2 theta given the information about theta. So we're given that the cosine of theta equals 3/5. The sine of theta is less than 0. Find sine theta, cosine 2 theta, and tangent 2 theta. And the only reason why they're telling us that sine of theta is less than 0 is so we can get the proper quadrant. So we need a quadrant where the cosine is positive, which would be the first and the fourth, but the sine is negative. So that means our theta is in the 4th quadrant. So first up, we're going to find the cosine of 2 theta. Remember I said there's 3 forms of this identity? How do you know which one that you're going to use? Depends on what the given information is. We're given that the cosine equals 3/5. So the best identity for us to use is 2 cosine squared theta minus 1. Why? Because all we know is the cosine, and that's enough for us to figure out the cosine of 2 theta. So that's 3/5 squared minus 1. 3/5 squared becomes 9/25. So that's 18/25 minus 1. and our sine of 2 theta, cosine of 2 theta, becomes negative 7/25. Again, we'll go ahead and highlight that answer. Next, we need to find the sine of 2 theta. So the identity that we learned is that the sine of 2 theta is 2 times the sine of theta times the cosine of theta. However, we don't know the sine of theta at this point. Well, that's when our good old friend, the Pythagorean sine squared plus cosine squared equals 1 is going to come back into play. Sine squared, cosine squared was 3/5 that we were given. Sine squared plus 9/25 equals 1. That means that the sine squared equals 1 minus 9/25. That makes that 16/25. And then we'll square root both sides. And since we've determined that the sine of theta, we're told that the sine of theta is less than 0, that means we're going to take the negative square root of this, and the sine of theta is negative 4/5. I'm going to highlight that. It's not the final answer yet. So now we can go ahead and find the sine of 2 theta as 2 times the sine of theta times the cosine of theta, negative 4/5 times 3/5, and our sine of 2 theta becomes negative 24/25. Now, the third thing we have to find is the tangent of 2 theta. Well, we've got a couple options for how we can do this, and I'll show you both ways. We still remember that the quotient by quotient identity that the tangent is the sine over the cosine. So it's the sine of 2 theta over the cosine of 2 theta, which we already figured out what both of those are. Crossing off that. And the tangent of 2 theta will be 24/7. We could have also done it if we wanted to use the new double angle identity that we learned, which is that 2 tangent of theta over 1 minus tangent squared of theta. Now, be careful because I've tried to do this about 3 times and I keep messing it up. We don't know what tangent of theta is yet, but we can find it rather quickly because tangent of theta, remember, is the sine over the cosine, where the sine is negative 4/5 and the cosine was given to us at 3/5. The tangent is negative 4/3. So we'll plug in negative 4/3. We'll go through and do all the math. So that's negative 8/3, 1 minus 16/9. So that'll be 9/9, so that'll be negative 8/3 over negative 7/9, which will then go ahead and multiply by the reciprocal of the denominator, negative 9/7. We can cancel this out, making that become negative 3. And we get the very same answer that we got the other way. The tangent of 2 theta is 24/7. And that's the first of the examples of what I expect you to be able to do. Let's move on to example 2. Find the values of the 6 trigonometric functions of theta given that the cosine of 2 theta equals 4/5 and theta is between 90 and 180 degrees. So we're looking for sine, cosine, tangent, secant, cosecant, cotangent. So to begin with, well, it doesn't matter. I'm going to go ahead and find out what the sine of theta is. So we know the cosine of 2 theta And now I'm going to use this form of that double angle identity, 1 minus 2 sine squared theta. Why? Because I'm looking for the sine of the sine of theta. So the cosine of 2 theta is 4/5. So then we'll subtract the 1 over. So that's going to be negative 1/5. Then I'm going to multiply by negative 1/2. And I get 1/10 equals the sine squared of theta. Square rooting both sides, I get 1 over square root of 10 equals the sine of theta. And since we're between 90 and 180, that means the sign will still be positive. Rationalizing that, square root of 10 over 10 is our sine of theta. Now, before I get too far along, I'm going to go ahead and find out what the reciprocal is. So I'm going to highlight this part of this answer because that's going to help me to get the cosecant. Remembering that the cosecant of theta is the reciprocal of the sine of theta. So if I take this 1 over the square root of 10 and take its reciprocal, I get just square root of 10. So it's easier to do this if you take the unrationalized form. Yes, you have to rationalize your answer and make it square root of 10 over 10 for sine, but use the unrationalized form and just take the flip of it. Okay, options. We've got multiples here. Okay, I know sine of theta, I know cosecant of theta. So I'm going to go ahead and find my cosine of theta. And the cosine of theta, well, I'm going to come back to our dear old friend here that we use so often, cosine squared plus sine squared, where the sine is square root of 10 over 10. So the cosine squared of theta would be, squaring that would give me 10 over 100, which is 1/10. So I'll subtract that over, making that 9/10 because I make that 10 over 10. And then square rooting, I get the cosine of theta equals 3 over the square root of 10. And again, remember that theta is between 90 and 180 where the cosine is negative. And then I'm going to rationalize that out. Negative 3 square root of 10 over 10. And again, just like before, when I found the cosecant by taking the unrationalized form and its reciprocal, we can do the same thing here. We'll find the secant of theta by simply taking the reciprocal of the cosine of theta at this point. Let me rewrite that so it doesn't look so sloppy. Secant of theta negative square root of 10 over 3. And again, that's a final answer, so we're going to highlight that in yellow. Almost there. We have 2 more to go. First up being the tangent of theta. By the quotient identity that we use so often, it's the sine to the cosine, where the sine is square root of 10 over 10, and the cosine is negative 3 square root of 10 over 10. Canceling off the denominators of both the common denominators of 10. Then we can cancel off the square roots of 10 and the the tangent of theta is negative 1/3. And finally, we need the reciprocal of that for the cotangent, because the cotangent is the reciprocal of the tangent. In this case, negative 3. And we're done with example 2. Yes, we still like to verify all of our identities like we did the other day in lesson 5-2. So we're going to verify that the following equation is an identity. The cotangent of x times the sine of 2x equals 1 plus the cosine of 2x. So again, we need to pick out the side that we're going to work on. In this case, I think this side looks the simplest, so we're going to work on the other side. So I'm going to highlight this because that's our goal. So if you remember, we said that it's easiest sometimes to rewrite these in terms of sines and cosines. So the cotangent of x would be the cosine of x divided by the sine of x. And the sine of 2x would be 2 times the sine x times the cosine x. Go ahead and put that over 1 so I got common denominators. Multiplying that together gives us 2 cosine squared x. And again, you have to be able to and comfortable working with these identities in multiple forms. So remembering that the cosine of 2x is 2 cosine squared x minus 1, if I add the 1 over, we get the cosine of 2x plus 1 equals 2 cosine squared x. So we can now replace 2 cosine squared x with 1 plus cosine 2x, which is our goal. Now in my graduate class, I have to write this a lot. Hence, the identity is proven. All right. So moving right along today, we'd like you to be able to kind of work our way backwards a little bit. So we'd like to be able to simplify expressions using double angle identities. In this case, we have the cosine squared x minus the sine squared x. Well, you should recognize that that is the cosine of 2x. Cosine squared x minus sine squared x. So our x in this case is going to be 7x, so it's going to be the cosine of 2 times 7x, and it's the cosine of 14x. Here we have sine 15 times cosine 15. Well, it's not quite what we need, because remember the identity that we're looking for is probably going to be this, that the sine of 2a equals 2 times the sine a times the cosine a. But we're going to create this, because 1/2 times 2 is 1. So we're not changing the value by writing this out. Put my pen back here. And then we're going to rearrange this just slightly with our parentheses, moving this over. So 1/2 times 2 times the sine of 15 cosine 15, which is the sine of 2 times 15. 2 times 15 being 30 degrees. 9 values you have to know by heart. Sine of 30 is 1/2. This simplifies to 1/4. Let me go ahead and highlight those answers. Okay, lots of stuff we're throwing at you today. In example 5, we'd like you to derive a multiple angle identity, writing the sine of 3x in terms of the sine of x. Well, kind of how we started this whole process out. We're going to think about how we could do this. And remember we said that when we started this, we had the sine of 2a, and we thought about it as the sine of a plus a. So similarly, we're going to start this with figuring out what the sine of 3x would be. Well, 3x, I think you'll agree with me, is 2x plus x. Now we can use our double angle identity, or excuse me, our sum identity, which is sine of 2x cosine of x plus the cosine of 2x times the sine of x. The sine of 2x is the identity 2 times the sine of x times the cosine of x. And there's that extra cosine of x. Now, we're trying to write this in terms of sine of x, which means that when I go to look at my double angle formulas for cosine, I want to use the one that's got sine squared in it. So I'm going to use 1 minus 2 sine squared x. Again, I'll go all the way back up here to the very first page when we talked about those. That's the one that I want. Get back to where we were. Here we go. So that's going to become 1 minus 2 sine squared x times the sine of x. So if we go ahead and do our multiplications through, 2 times the sine of x times cosine squared of x plus the sine of x minus 2 times sine cubed of x. So we distribute this. Remember our question said to find this in terms of sine of x, so therefore we got to replace cosine of x. And welcome back, my old friend, to cosine squared plus sine squared equals 1, which means that cosine squared of x equaling 1 minus sine squared x. Plus sine x minus 2 times sine cubed of x. We're almost there. So we'll distribute this in. And then finally we can combine our like terms. 2 sine x plus sine x is 3 sine x. Combining our sine cubed x's. And we have successfully written the sine of 3x in terms of just sine of x. But wait, there's more. Next up, we're going to add some more identities in for you today. And that is the product to sum and the sum to product. These are very important for us that we use these identities when we get into calculus. So we can add the corresponding sides of the identities for cosine of a plus b and cosine of a minus b to derive a product to sum formula that is useful in calculus. So cosine of a plus b plus cosine of a minus b. Well, here's the cosine of a plus b. Here's the cosine of a minus b. So if we combine our like terms, notice that these cancel out. Cosine A, cosine B. These are like terms. These are like terms, and they're going to be opposites to each other, so they're going to cancel away. And we get this. And then we divide this 2 over to the other side, multiplying by 1/2. And we get the identity that the cosine of A cosine B equals 1/2 times cosine of A plus B plus cosine of A minus B. Product to sum. Similarly, if we subtract those from each other, again, here's cosine of A minus B minus cosine of A plus B. Here's the two identities. Again, we're going to have like terms. I went ahead and distributed this minus all the way through here. changing that to a plus sine A sine B, and we get this. Again, we multiply by the 1/2, and we get our second product to sum formula. So on your tab where it says product to sum in your flip book, we would do this. We would do the same thing with the sign identities. I didn't derive those. I just gave them what they are. So 4 new identities that you need to write down, and this goes into the product to sum tab of your flip books. And while you're there, in example 6, we'd like to use this product to sum identity as the sum or difference of 2 functions. So it's 4 cosine 75 times sine of 25. So that's going to give us as I go back and look through my stuff, it's right here. 4 cosine 75 sine 25. So here's cosine times sine. So again, we're going to have to do a little bit of manipulation to this. Actually, no. Hang on. Let me get this right. Okay. So here's what we're going to do. The cosine of A times the sine of B. Well, we're going to make a substitution for that. So that's 1/2 times the sine of A plus B minus the sine of A minus B. 4 times 1/2 gives us 2. A is 75 and B is 25. Again, watch your parentheses on these because they can get rather nasty. So now if I distribute that 2 in, our answer becomes 2 times the sine of 100 minus 2 times the sine of 50. So we've rewritten this as the sum or difference of 2 functions. In this case, happens to both be sine functions. Our final thing to put into the flip books, and I'm not going to present these, I'm just going to have you guys write these in your flip books. That is the sum to product identities. So basically we're going back up to here, and we're taking this 2 and putting it to the other side. The sine of A plus the sine of B equals 2 times the sine of A plus B over 2, cosine A minus B over 2. Again, I just want you to write these in your flip book. Final example then, write the sine of 2 theta minus the sine of 4 theta. So notice we're taking the sine of A minus the sine of B. So I'm going to use that identity. 2 times the sine of 2 theta minus 4 theta over 2 times the cosine of 2 theta plus 4 theta over 2. So that's going to be negative 2 theta over 2, and I forgot to write the word sine in there, so let me fix that. Sine of negative theta. 2 theta plus 4 theta would be 6 theta divided by 2 would be 3 theta. Even odd identities, sine of negative theta equals the negative sine of theta. So our final answer becomes negative 2 sine theta times the cosine of 3 theta. Welcome to double angle identities, also product to sum and sum to product.